Okay, so hi everyone. Today we are going to see InternVL 3.5, which is advanced open source multimodals in versatility, reasoning, and efficiency. So the why we choose this paper is because we wanted to have some open source multimodality available to be able to compete with commercial models. So every integration that you want to develop as an AI engineering, now the bar or the standard will require to have multimodal capabilities. So having this addition and see how it works is what it will be is what will make you compete into the market. So this paper not only provides how they did it, but also gives tips for the developer community to actually improve in their workflow in general. So this paper is really good about it. And so just things to keep in mind while I'm going through the slide. The gray slides will be things that are not in the paper, but I find it helpful to explain so we can kind of have something or have some baseline for explain what I saw in the papers. And also I prepared a notebook for inference that will be referencing when we need it. So let me start here. And also we will have breaks between sections so we kind of go over questions or ideas that you want to share. So the overall idea is that you want to have a multimodality, and this compose about text and image. So you put your image, you put your text. So we wanted the image be processed by this InternVL 3.5 and the text processed to the language model or the language capability, which in this case would be QN3 and GPT open source. And we wanted to be this versatile, have reasoning capabilities, and be efficiency. And that's what this old paper is about. So we are going to dissect those three core functionalities of the InternVL 3.5. So like I just prepare this type of this response so we can kind of understand what are the differences. And you see we have four different type of response based on the different models that they provide or at the different stage that they provide at the model, and you will understand that more in a bit. But this is the response of pre-training, and you will see the picture that I'm reference to later. But just keep in mind the different type of response. This is a dog sitting on a rock in front of a building, and the instruct model, which is the next stage that they did, is a fluffy white dog wearing a rainbow costume with a leash sitting on a rock surface under a clear blue sky with a shore visible on the background. And then the next stage for them was the response that they provide for the next stage is small white dog dressed in a colorful rainbow outfit and wearing bunny ears and standing on a rocky surface. And you get the idea that they get different type of response at different stage. And the reason why all sounds, I mean, reasonable within a picture of a dog in certain position is that they initialize with the already language capabilities from the open source. So even though that they might not understand fully the picture, you might get the impression of a working solution. So that's why they run a lot of experiments to actually understand if this is going somewhere or it was the language making you believe that it was a reasonable answer without knowing without really understanding the picture. So yeah, so I hope that would be helpful as introduction. So let's go to the abstract. And this the InternVL 3.5, which is a new family of open source multimodal models. And this advancing versatility, reasoning capabilities, and inference efficiency along the InternVL series. And the key innovation that they did is that they add a cascade reinforcement learning framework, which enhance reasoning through a two-stage process: offline reinforcement learning for stable convergence and online reinforcement learning for refined alignment. And you will see, for me, this was one of the most brilliant ideas that they provide, and we will see this in detail. And the other thing was that they proposed a visual resolution router. And I was impressed by this because it's so simple but so effective that you can incorporate in your workflow on whatever you are doing. So it's one of those things that make you think why I didn't think about it, or because it's so simple but it's so effective, and that allows to dynamically adjust the resolution of visual tokens without compromising the performance. And they also separate the vision from the language server, so they deploy in different parts. It's not in a sequence, is they run it in parallel. So they separate the vision encoder from the language model across different GPUs, and this is what adds the efficiency of the model in the training and the inference stage. So yeah, so those are the three core ideas: enable reasoning through cascade reinforcement learning, adjust dynamically the vision resolution token, and separate the vision from the language model. So this is kind of to give you an overview on the overall performance. And the key thing about this graph is that they are able to compete with the most or the latest commercial models like GPT-5 or Gemini 2.5 Pro. But also they are able to do it across the different release that they did. So you see here that we have InternVL 3.5. This is the most advanced model that they released, but they release also other models, which gives flexibility to developer to use in different areas or in different settings using different computational capabilities. So this is one of the advantage of this paper. Okay, so they have three main contributions. So the first one is the release of the InternVL 3.5 series, and through our series of models that goes from 1 billion to 241 billion, and in both dense and mixture or of expert models. Also, they include cascade reinforcement learning and the visual resolution router and the coupled visual from the language deployment. And also they are able to compete with the commercial models available like GPT-5. So was the main addition that they have. So any questions so far about the introduction? Okay, cool. That's okay, so let me go through the architecture. So this is where we are going to spend the most amount of time on this discussion. And you see in the middle that we have the core architecture of InternVL 3.5. And as you can see, we have on the sides, we have a close up through two different things. One is a dynamic high resolution, and the other one is from the visual language connector. So essentially what we are doing here is that we are processing the image. So we have an image and we process that image. And based on the height and width of the image, we process that image into a predefined aspect ratio. So we don't process any image with their initial height and width, but we process and we use our predefined height and width based on what they did. And let me show you what I mean by that in this notebook. Okay, so can you see the notebook, right? Okay. So here you see we put the image and we have this function that is find the closest aspect ratio. So it doesn't have any intelligence. It just look your width and height of your image, and based on that it has the dynamic processing, which is those those predefined aspect ratio that I provided you, and at the end we provide a process image. So I use a picture of my dog, which is the one that I show you at the beginning. So you can see the blue sky, you can see it has a rainbow costume, and this is the building or the church in the back. And when we process this image, we process the image and we go through patches, and those patches are with predefined aspect ratio that I will show you on this dynamic high resolution. Okay, so we pass the image. Now we know what is a predefined aspect ratio, and there is no intelligence in that. It's just a bunch of if and else statement, and it defines what's the closest ratio. And based on that, now that we process the image, we can put it into the vision capabilities of the model, so we can translate to a more to go through the LLMs. But before we go through the LLM, we need to process this image. So we can kind of need a understanding on what the image is about, right? So we process that image. The way they did it, they have two different through different ways of doing it. The first one, and that's the default one, is just they grab the tokens of the patch of the image, and from then they perform a pixel shuffle that compress the image from 1024 tokens to 256 tokens. So with this pixel shuffle, but the brilliant idea, and that's why I mentioned at the beginning that it was one of the ideas on why I didn't think about it, right? Is that they have this visual resolution router, and this is a classification model. This is the classification model that decides if you need a high resolution or a low resolution based on a semantic meaning. And let me show you what I mean by that. So you see this picture of my dog, right? And you see that these patches, they're not the same. They contain different meanings and different ideas, right? So for instance, here is a blue sky, no matter if I see it in a low resolution or if in a high resolution, right? But this, it has the face of my dog, and it has the color, it has on the back, it has the church. So I will say this has more semantic meaning that this one, and that's essentially what this classification model does. It tries to understand, okay, do I need this in high resolution, or can I just use low resolution, and the model will be able to understand either way, or perhaps I need some details about it on this image, and perhaps I need to capture more about the image. So that's how they decide. You go with this visual resolution router and decide, okay, this patch is a high resolution, or this patch is a low resolution. And with this idea, they are able to reduce to 50% the tokens. And so the compression after the when you go to the MLP projector is 64 tokens compared to 256 tokens. So this was one of the most things that impressed me, because it was so simple to put it, and yet they were the one that they did it, and they don't like the most important thing about this is that any they don't lose information, but it reduces the inference time a lot, and we will see on one of the latest experiments that they did. So after we have that image already processed, and then if we go to the connect, when we have the connection between that image, between the image, we can now pass to the large language model, which will be this open source model, GPT open source or Qwen3. And from then we provide an answer, right? And that answer, as you can see, you see here, this is a chat message, this is a text tokenizer. So this runs in parallel, and we will see that more in details, but the idea that I want you to take from this is how they process the image and how they did the visual resolution rather to spend less token and to speed up the process. And then that they run the architecture in parallel. They run the vision and the language side by side. So this is not part of the paper. This is just research that I used to put this together. But the core idea of a pre-training is that you get a full body of knowledge. It can be text, it can be code, or it can be image. And you want to predict the next token. So given a sequence of token, you predict the next token. That's the pre-training stage. So it's on level corpus of data. And with the post-training, you actually add capabilities to the model. So that's the core idea of the pre-training and the post-training. Now we are going to understand what they did at the pre-training stage. So the first thing that they decide is that they are going to use the next token prediction loss, which is given the sequence that we have here, and this is a multimodal sequence. So you have text, you have image, yeah, text and image. You have a sequence, and then you want to predict what's the probability of having this token. So this token. And you apply the negative log probability of this. Given this sequence, what's the probability of having this token? And you apply the negative log probability to that, and you want to minimize that. So this is the negative, this is the next prediction, the next token prediction loss. And to mitigate bias to longer or shorter response, they just square average to reweight this and to avoid having bias toward longer or shorter response. The data for the pre-training stage was mostly private data, proprietary data from them. So they use multimodal data and mainly image captioning, general Q&A, and text-only data from the InternVL series, and they augmented that data with open source data. But this data is private, and they have 160 million samples, which is around 250 billion tokens, and the text multimodal ratio is 1 text from 2.5 multimodal. And they applied the max sequence length was 32,000 tokens, which is around 48 pages. So just kind of to give you an idea. So this is to account long contextual understanding and reasoning. Okay, the post-training stage, and this is the secret sauce of this paper, the post-training. So the post-training has 3 phases that we are going to go one by one, but they have the supervised fine-tuning, the cascade reinforcement learning, and the visual consistent learning. And as I show you in the architecture, they have 2 ways of doing of the architecture. One is with the flash model that use the vision resolution router that I explained you, that use the classification model to decide if you want high resolution or low resolution, and the other one that doesn't have that you have the 2 approaches and they test both, and we will see that. Okay, so let's start with the supervised fine-tuning. So the supervised fine-tuning, the objective function is nest token prediction loss and the square average to avoid avoid bias, and they use a context window of 32,000 tokens. And the data that they use instruction following data from InternVL3. They use multimodal reasoning data, which is thinking data, and capability expansions. We will see in details what this data is about in a later section, but for now, that's the overall of the supervised fine-tuning that they did. This also not part of the paper, but just so we can kind of go into the same picture. The offline learning in reinforcement learning for large language models, what it does is that you have a prompt, and you have a response. So you have your CSV file, you have prompt response, and you test that, and you create a reward. And so there is no generation in the offline learning. While the online learning, you have the prompt, and from that prompt you generate a response. So that's the difference between one and the other. And as you can see, like, this has difference in computational time and in computational resource that they mitigate. This was on the most clever things that I saw from the paper, because they was able to mitigate this type of computational difference between one and the other, and they take advantage. They took the best of both worlds, essentially. So now let's go to the cascade reinforcement learning. So this cascade reinforcement learning has two stages. One is MPO, and we will see what this means, and the other one is GSPO. Let's start with the first one, with the offline reinforcement learning. So to give you an idea, this reinforcement learning, what it does is that introduce negative samples to prone low quality regions. So something that the model is bad at, or is giving bad response. The advantage of reinforcement learning is that it also shows you negative samples, rather than supervised fine-tuning only shows you good examples. The reinforcement learning also shows you bad examples, so that allows to enhance the overall quality of the model. So usually offline reinforcement learning algorithms offer a higher training efficiency, but the performance is so it is cap or is lower compared to online reinforcement learning methods. But the online reinforcement learning methods allows to have, is time consuming and is expensive to run, because you generate the response through each prompt. So for the offline reinforcement learning, they use a mixed preference optimization, which is composed by preference loss, quality loss, and generation loss. And they try to that's the loss function that they use, and they try to reduce that with this offline reinforcement learning. Okay, now we go to the GSPO. And before I jump into the GSPO, I wanted to show you this, so we can kind of understand where these things come from, and we understand the math behind that, or the math formula. So let me give you an example. Let's say you have a prompt, and you ask the prompt, what's 12 times 13? So this 12 times, or this prompt goes to a policy model. This policy model, what it does is that it generates several responses. Like you can see here, one response, another response. And once you generate several responses, those response goes to a reference model. This reference model, what it does is that it tries to keep your policy, your generations within the boundaries of the gains that you get through the supervised fine tuning. So we don't want to deviate a lot from what we already gained through the previous stage to the previous stage, like the pre-training or the supervised fine tuning. So we want that the model behaves within a central range, and for that we use Kyle divergence. So this is the purpose of reference model, to understand if one of the response is deviating a lot from the original model, and it penalizes the model for that. And the other thing and we have another model, which is a reward model. What it does is that it evaluates each of the response, and it generates a reward for the response. Let's say for the first one, which is the correct answer, it shows that is plus 10. And this one, is a wrong answer, so it's minus 5. And this one is a right answer, but it's providing information that I didn't ask. So it's better than a wrong answer, but it's not the best answer. So when we wanted to have it in a lower rank, so we put it on plus 8. After we had the reward for all the response, this goes to a group calculation, which is taking the average of this reward and take the standard deviation and subtract each each mean and standard deviation from the reward that you have here. So it's kind of like a C-score, but you here is called the advantage. So that's the advantage of the model. So it's 5 standard deviations away from the mean of the overall response that you generates, and these go back to the policy model. The main difference between the GSPO and the GRPO, which is the previous one, the GSPO was introduced by DeepSeek recently, and the main difference with the GRPO, which was used previously, is that this is applied to the sequence. So this sequence 12 times 13 is equal to 156. The advantage is applied to that sequence, to the full sequence. And rather than the GRPO, it was applied to each individual token. So this applied to the sequence allows stability to the model, and that it doesn't deviate much from the already gains. Now that we understand that, let's go to understand the math. So remember that I told you that the advantage was just taking the mean and the standard deviation away from the actual result. So this is the reward, this is the prompt, and this is the response. So this is what I told you that it was plus 10 for the right answer. And you subtract the mean from all possible answers for all possible rewards. And then this is the standard deviation of all possible rewards. So it's just taking the mean and the standard deviation. And that's the advantage that you then go to the calculation. And the same goes here. Like it has a lot of things in it, but it's not that complicated. Here, the clip, like this is the what I mentioned, that it was trying to keep the model within a standard behavior. So this, what it does is that it evaluates how much you are deviating from the answer, and it tries to keep the answer within a certain range. So this is essentially the divergence that you have from the model, and this is the advantage that you got here. So this is exactly what I explained you on the previous slide, but just with the math formula. And this is the expected behavior from the old model, and this is the minimize the divergence of the model, and like try to push more for the high advantage results and penalize for the high divergence response. So what this cascade reinforcement learning, so this, you go to the MPO, this is the first stage of the offline, and then with those gains, you go to the GSPO, which is the online. And that has a lot to do with the data that we will see in a bit, but essentially is a two-stage process that the GSPO or the online reinforcement learning takes advantage of the offline reinforcement learning, and that speed up the process a lot. And the overall idea is that this cascade reinforcement learning that they propose has better training stability, and the performance gains achieved through the MPO stage enhance the stability of the GSPO stage. And yeah, and reduces sensitivity of the model, improves the training efficiency, and it has higher performance ceilings. So the models with fine-tuning with MPO take fewer training steps to achieve higher performance in the later stage of the reinforcement learning. So this is the final stage of the post-training pipeline. So you have here, remember that I mentioned that we have two ways of doing this. So this is the visual. So this is the visual consistent learning, and this is the InternVL 3.5 Flash. So they call flash to the one that they actually put the visual resolution router, which is a classification model that tells you if it is high resolution or low resolution mode or low resolution requirements for the patch of your image. So this visual resolution or visual consistent learning has two stages as well. It has the consistency training and the router training. So let me try to explain this formula so we can kind of know on the visual consistent learning what it does. So the first step is the consistency training. So remember that I told you that this is a picture of my dog, right? Like that I show you in the Kaggle example. So what I did is that I divided into patches, and here we have a reference model. So this reference model will put the image in high resolution. So all image that I put into the model, it will create high resolution patches of the image without this visual resolution router, so by default it would be high resolution. But then we have the policy model. The policy model, what it does is that it creates a uniform sample that goes through high resolution and low resolution. So it adds compression and it has a high resolution. It has two versions, right? So let's say this is the low resolution and this is the same image. So let's say this is a high resolution, right? So this KL divergence compares the reference output with the policy model across the different compression rates of the image, the high resolution and the low resolution. And they do this for all examples that you have. So the goal is to minimize this divergence. Essentially, is answering the question, if I put this in low resolution, do I lose meaning in the picture? So if the answer is yes, I might have to do something different. And if the answer is no, I can compress this patch. So this is, now that they have that, they go to the second stage which is the router training, and it is a binary classifier. What they did is that they leave everything constant. So they freeze the InternVL3.5 and the language capabilities and the projector, and they only change the visual resolution router because this is my assumption. As you can see in the first slide that I showed you, that it has the different response. It's difficult to actually tell what's the best model or not, because given that it has good language capabilities, it can fool you to think that it's actually understanding, and perhaps it's just inference based on what it grabs from the image. So they leave everything constant, and they tweak the visual resolution router. And you see here, this is the high compression. This is a high compression image or a low resolution image, and this is a high resolution image. And they evaluate how much impact does this have. This is just a ratio, and it compares how much you lose of the information based on the compression that you did. Any questions so far?
Yeah, may I have a short question?
Yeah.
I'm wondering if I understand it correctly, but do I like, is it true that the idea of this task is to split an image based on the semantic value? So like I will ask based on the little bit physical properties of a material, because this is what I'm working on mostly. So if I have, for example, the volume representing some kind of density, phantom, like water with something, then this algorithm converts this into a different sizes of patches with different resolution depending of the heterogeneity of the certain region. Is it correct?
No,
So
so Yeah, so the first stage they create they have a predefined aspect ratio based on the height of width of the image. So without going to any understanding of the image, based on the height and
Okay.
width of the image that you put there, they will decide which one is the best aspect ratio. So they kind of classify the image
Okay.
based on that. But then when you go to the visual resolution router, which like the whole purpose of this visual resolution router is to make more is to be efficient in
Mm-hmm.
terms of the capabilities of your of your resource that
Mm-hmm.
I will explain that in a bit, but they buy into patches the image as I show you like with the picture of my
Yeah.
dog and decide which one of those patches needs a high resolution or a low resolution based on the semantic meaning, and for that
Okay.
they use this
Yeah.
form. Yeah.
So in principle, how much information do you need to encode and information? How much data you need to encode and semantic information of the image,
Yeah.
based on the what is on the image? Yeah. All right. Great.
Exactly,
Yeah.
but yeah, this is a machine learning algorithm. So
Yeah.
we like what I show you here is the training stage, but when you
Mm-hmm.
go to the inference, so that doesn't happen. It recognizes through the machine learning algorithm if you need a high compression or not, but it doesn't decide based on your image in particular
Okay.
because it already did on the machine learning stage,
Yeah.
calculating the cross entropy loss and everything.
Yeah. Thank you.
Yeah. Any other question?
Pastor, I had a quick question. They
Yeah.
use the term pixel shuffle.
Yeah.
Is that the method they're using for their compression? I know it was right in that picture, it's kind of in the upper right, but the compression actually happens before then. So I wanted to see if that's just something different.
Yeah. Great question. So they actually have two versions of this, like of so they have the InternVL 3.5 and the InternVL 3.5 Flash. So the whole idea of the Flash is using the compression through this vision resolution router. So you go from a patch that has 1024 tokens to 64 tokens. While in the pixel shuffle, which is a compression method that they use in the other version of the model, they compress from 1024 tokens to 256 tokens. So this visual resolution router, what it does is that improves by over 50% the tokens that you will use without using this visual resolution router. So there are two versions of the model, and they compare both. I will show you it when we run when we see the experiments. But they have two versions of this model, and the whole purpose of using visual resolution router is to speed and efficiency of the resource.
And is the compression then used in that visual resolution router also pixel shuffle?
No, so the compression on the visual resolution router is made through deciding high resolution or low resolution.
Okay, thank you.
Yeah. Any other question? Okay, so the data that they used for supervised fine-tuning was in structure following data from InternVL3, and it was reused from the previous series of model. And also they use multimodal reasoning data, which is thinking data for having long thinking capabilities. And also they use capability expansions data sets that includes general user interface interactions and scalar vector graphics. So this data is private. The supervised fine-tuning data is private, but the cascade reinforcement learning, this is open source data, so we do have access to this. So for the offline reinforcement learning, we use the MMPR v1.2, and it has 200,000 sample pairs. But for the online reinforcement learning, and this is what I mentioned that we take advantage of the offline, is we use the queries that was between 0.2 and 0.8 accuracy on the offline reinforcement learning, right? So we take a sample of that plus multimodal data set, and they construct a new data set that is MMPR tiny, which has 70,000 sample pairs. And this is how the MMPR V1.2 looks like. So you have your image, you have questions, you have the chosen response, and you have the rejected response. That's why I mentioned that on the online or the reinforcement learning shows you negative examples as well, so you can prone low quality regions. This is what I mean by that. This, you have rejected response and you have chosen response. And this is how the data set looks like. It's available in Hugging Face. You can see questions chosen and rejected. So you can see, you can use it right now if you want it. And for the online, this is the MMPR Tiny. We do have access to this also in Hugging Face. So we can generate, with a prompt, we can generate a response and replicate everything what they did. And this is for the vision, the vision router that I mentioned. We had consistency training. For it used the same data set that the supervised fine-tuning, and this they did it to retrain the original performance of this stage. And for the router training, which is they use a subset of the supervised fine-tuning composed primarily on OCR and VQNA examples. And yeah, so this enables resolution router to learn how to dynamically decide the compression of the image. So the test time scaling, so this is for reasoning capabilities. So they actually said in the paper that this didn't add improvements to the model. They only use this for reasoning benchmarks, but it's not part of the model that they released. They only use it for reasoning benchmarks. So not much to say about this time scaling. Now, this was also a brilliant idea that they did. So this is the coupled visual language deployment. So usually you have your image and you have a text like describe this image, right? You put the image and describe this image. So you have the image and you have the text component. So the idea is that this goes to a vision model, and the vision model processes the image, and then from this processing goes to the LLM after it's processed. So it goes in sequence. You process the image, then go to the LLM, and then you create the response. And you do this in sequence, right? Process the image, read through the LLM, and as you process, it goes to the LLM until you get your response. So what they did is that they did a efficient way of doing this by separating the vision from the language. So you put your image and say, describe this image. You have your image and you have the text. The text goes to the LLM and the image goes to the vision of the model. And they have a connector, but both are different servers, and those servers have their own GPUs, and they don't, you don't share environment between the language and the vision. So as you can see, as you process, you connect with the language, and as you process, you go to the language, and this is already preparing the response. So after you complete creating or passing the image, the process image, you already have your response because it's processed in parallel. So that was one of the key things for this paper that actually improved the time in the inference time, because this is for the inference, but also it serves for the training when they were running through the model, right? So it allows to speed up the process a lot. So what?
Pastor, quick question on the previous slide. So
Yeah.
main speed up on the language model side is that the encoding is now faster. Is that it? Because the generation still has a dependency on the VIT and the MLP, right?
Yeah.
Okay.
Yeah. So do you like the encoder is not faster, and what do you mean?
Because in the lower half, the input message, essentially
Mm-hmm.
VIT and MLP is encoding the image and the LLM is encoding the text. But in order
Mm-hmm.
to generate the response, there's still a dependency on both. So, and my understanding is that the generation of response is the one that takes the most time, given how relatively short their instructions are relative to the output. So, or how does it, or am I misunderstanding it? Because I see that the communication, the yellow blocks, it seems to be interspersed.
Yeah, so what I understand from the paper is that in like with this approach, they process the image and then goes to the large language models. So after the image is already processed, right? But with this approach, they process image and they connect the image at the same time, and they already preparing the response. So like for instance, with this picture, right? You see that we have it in patches, and let's say we patch this, and that's the one that we patch first. They already will be preparing the blue sky. Like that's why I understand perhaps it's oversimplification on what is actually happening. But
I
what I
see.
understand is that it's generating the response as you are processing the image without waiting for the full processing of the image. I don't know if that makes sense.
That makes sense. Thank you. That clarifies a lot. Thank you.
Yeah. Awesome. Awesome. So yeah, so this is the yeah, so this is the this is a picture of the protagonist of my story, right? So we go to the vision model, the image goes to the vision model, and then the text goes to the large language model, and they preparing the response side by side. So whenever the picture is already processed, we already have the our answer. A fluffy white dog wearing a rainbow costume with a serene rocky surface, wearing under a blue sky with a church visible in the background. So it doesn't have to wait to have all the meaning. He's preparing the response as he processes the image. Questions so far?
I have a question, actually. Can you go back previous slide?
Yeah.
So in this example where you're showing your dog, and there's like please describe this image shortly. That's like a prompt that carries along with it, right?
Yeah.
And so like, does the paper talk about the weighting between the textual prompt that comes with the image? You know, like how much of a difference does that make? Like, or are they just encoded separately and fed back in?
No, so I didn't saw anything about describing the or separating like what your prompt was based on the image.
Mm-hmm.
I didn't saw anything related to that, and
So follow-up question, like you showed in the Kaggle notebook that your dog picture, it's a great picture by the way, was like rearranged with the patching, right? And so like you got the dog's head in a different area, like the patching, the repatching, let's say, of the image, that's all happening independent of any prompt. Like it's doing feature extraction in a sense, right?
okay,
That's like I guess a subsidiary question.
now I understand. Yeah, so this is independent. So you process your image through this vision model, but
Yeah.
that's independent on what you are providing here, right? Like that's and yeah, I mean that's a great question because if you ask for details, perhaps or details about the
Right. Couldn't
nodes,
it? Yeah,
you
it
might
would influence how it does that patching step. Like
yeah.
as the model, like if I was like, if the prompt instead was what colored jacket is this dog wearing, then I would only focus immediately on the jacket part. And like I don't know, like I just feel like that would have sped up the process.
Yeah. So I really don't know. Perhaps like it is interesting question because like you that there would be other regions that might not that important,
Right.
right? So yeah. I really don't know if they account for that, but it would be interesting to test definitely.
The
If
paper
I
largely demonstrates
may,
how it could do it on its own.
Yeah.
if I may, like the patching is part of the vision transformer. So that's just like when you're creating different tokens, the issue with the image is that you divide it into different batches sequentially. So you will lose, context of the patches being close to each other as you go horizontally and then go back, etc. So that's my understanding of creating different patches. But I have a different question because you showed me for any image, you have a question and then a correct answer and wrong answer. So in this case here, for your question, please describe this image shortly. I know what is the right answer, but what do you actually provide a wrong answer for training or measuring the performance? What wrong answer could you say?
Yeah, so actually that's the training pipeline. So on the training pipeline, the data set that they use does have the wrong answers. So is on the data set that they use for the reinforcement learning or the cascade reinforcement learning that they did. So in this stage, we are using as inference. So it doesn't have a wrong answer per se because you are running. It's like you provide this to ChatGPT and get a question. It's the inference stage. But on the training stage that we did to this actually work like it is working right now, they did use negative negative examples based on the data set that they use, but it's on the data set that they use on the training stage in the reinforcement learning portion.
I understand that was in training, but if you had an idea, if you looked at this training, what would be a wrong answer for such a question? But if you don't know, that's okay, because we can look at that later on.
Yeah, I mean, for me, a wrong answer would be that if it is a ugly dog, I wouldn't agree with that. So yeah, so something that perhaps doesn't describe as much. And as I show you, let me show you this really quick, where I compare the different models. You see, like one thing that I didn't like is the oversimplification because it's a dog sitting on a rock in front of a building. I mean, that might be a wrong answer, right? Because it's not a building per se, or like I would say it's a bad quality response. And this is response of the same model, but on the pre-training stage, it didn't go through the supervised fine-tuning, and it didn't go to the cascade reinforcement learning that we did. So yeah, I mean, that would be an example because it doesn't fully understand the image. And also when I say shortly, it describes every single detail on the MPO stage. So that would be also an example of a not good answer for me, at least. Okay, so I won't go through details of all experiment. I just select few experiments that was instructional for various purpose. But the overall idea is that they run a lot of experiments, and most of the experiments that they run actually have a good performance across different benchmark that they use. So I just pick few experiments to demonstrate what they did and how this can be useful. So you can see here 4 different versions of the model. So this experiment was trying to prove if the cascade reinforcement learning actually work. and if you actually need it. And as you can see, in all versions of the model, it performs better in multimodal reasoning and mathematical benchmarks. So the cascade reinforcement learning was a good addition in terms of providing of providing good performance. And this is a core experiment because it allows to demonstrate why going through the cascade reinforcement learning matters. And what they did is that they compared the effectiveness of the instruct model with the MPO stage. That, remember, is the first stage of the cascade reinforcement learning, but also they break down between running only the MPO, running only the offline, running only the online 2 times, and then running only the cascade reinforcement learning. And the results are remarkable because with the MPO you can get a lot of performance, a lot of increase on your performance, and it doesn't use a lot of GPUs, so a lot of GPU hours. So it was a great a, a great a great addition. But with a GSPO, you still have performance gains, but at the cost of thousands of hours of GPU usage. And that is if you run it, if you only run one time. But if you run 2 episodes of GSPO, you get up to 11,000 GPU hours, and with just 1% of performance gains. While using cascade reinforcement learning, that, remember, use MPO, then GSPO, and the GSPO use as advantage the stability of the MPO stage of the offline reinforcement learning. You only need half of the GPU hours to get a better performance. So that's why adding the cascade reinforcement learning matters for this InternVL 3.5, and is one of the great contributions to the community to understand where the direction of the models can be to do it efficiently. So this is another this is another comparison, and this is a comparison of running Flash with running the default model. So remember that Flash use the visual resolution router that we mentioned, that it goes high performance and low performance, right? Or high resolution and low resolution with the image. So as you can see, it's not better in terms of performance, but it's not worse, or it's not a lot of worse. So, and is able to have a different a good performance without many costs, and is able to speed up the process a lot. And as you can see here, we have the resolution, different resolution of image. So we pass this image, this resolution of image, or this resolution of image, and we compare with baseline, the coupled vision, or the coupled the language from the vision, and also the vision resolution router. And this is the request per seconds. So as you can see, with this base, we are able to get more requests per second when we use the couple of the vision and the language, but also with this low resolution, high resolution model. So we are able to have more requests per second. And when we see that more is when we have a high resolution image like this one. When the baseline have 1.5, around 1.5 requests per second, we can increase to 5 requests per second, which is a lot for this model. Okay, so any questions? This was the final slide. So yeah. Let me see. Yes, yeah, thank you. Thank you, guys. Any questions, comments, additions? Yeah, like we get through to the hour by the minute, so yeah. Thank you so much, guys. I really enjoyed this. Thank you, thank you. A lot of fun preparing, so thank you so much.
Thank you. Bye bye.
Bye, bye, guys. Take care.